Hello and welcome to Khaliltronics. So we are on another chapter on the mechanical modeling. We are going to introduce a mechanical modeling element and its properties. Okay, so according to the table, we have an element that is spring. We have a spring, that is spring. We have a K, that's spring constant in Newton meter per meter, where X in the direction of X, where the X is displacement, is a distance traveling in specific directions, and the force, the applied force, it is in Newton. So whenever you have a spring and you want to find the dynamic properties of it, you are going to say the force, that's F of T in the direction of T, must be equal to the spring constant, that is K, and the X, that is distance in the direction of the T. So this is the first when the spring is applied. So by going to the next one, that's number 2, we have a damper. From here, a damper, that is the force F of V, and this is the first applied force F of T in the direction of T, in the direction of X, that's distance, displacement. So this is the damper and it is rigid. So whenever you want to find the force apply on it, you are going to say the force, that's normal force Ft, direction of T, must be equal to the force, applied force Sb, times the velocity. But in the direction of T, the velocity will be a first derivative, will be dx of T over dt. That's the first derivative with respect to T in the direction of X. So where the F of V is viscous frictional coefficients in Newton per meter per seconds, where V is normal velocity in meter per seconds. So this is the damper, this is the applied force, this is the X in the direction of X, that's the displacement. Okay, so for the mass, this is the mass, applied mass, this is the force, that's force, applied force, this is the displacement, travel in the direction of X. So if you want to find the applied force, that is F of T, we are going to say the mass, the given mass, this mass, the given mass, this mass, we are going to say mass times the acceleration, that's A, where A is a velocity per unit time. But remember, the accelerations is velocity per unit time. So since acceleration it is second derivative, we can say mass times d square x in the direction of T over dt square. So this is the properties, where m is mass in kilogram and acceleration due to gravity in meter per second square. So this is how it is. Like normally when you have, taking an example, when you have a spring like this, you have a K and you have in the direction of, let's say, y of T. So the applied force, this is for spring, so the applied force is going to be the K, that's the applied force F of T, will be equal to K, that's elastic constant, times the Y, that is displacement. The damper, for the damper, okay, so when we have a damper, that's f of t, while this is f of v. Pictures frictional coefficients, that's here in the direction of x of t, and here. So we are going to say f of t must be equal to the frictional coefficients, that's f of v, times, since it is in the direction of x and it is damper, we are going to say times the first derivative of x. Assuming that here it is y, let's change to y. We are going to say differential of y, that's first derivative. So for the mass, we have a mass body m, that's m, in the directions of x of y of t. So the applied force it's gonna be f of t must be equal to the mass times, it is, you know, the acceleration, it is in second derivative since it is velocity per unit time. So we are going to say d square of y over dt square. So this is the properties the properties of the element in mechanical modeling, and this is how it is work. So thank you for the watching. Don't forget to subscribe, give a like and comment, and share it to others. Thank you.